I'm ready. I will get it.
Okay, hello everyone. Thank you so much for inviting me to be here. So the topic today I'm going to talk about that is development of an electromagnetic energy harvester to power wireless sensor, which we use to monitor civil infrastructure, especially bridges. So this is a project when I was working on my postdoc. I was postdoc in City Units of New York. With the help of my advisor, Dr. Ali Azram, who is the PI of this project, we wrote a proposal about electromagnetic energy harvester. So thankfully we got the fund. And I'm the co-PI, the first co-PI of this project, and Dr. Hani Nassi from Radford University is the second co-PI. So the outline of this presentation includes introduction. I give introduction why we need to use this kind of technology. Theory and a basic concept, which I focus more on some mathematical formula, hopefully to rocket, and design, fabrication, and testing of the device. Based on that theory, which I'm going to present. And if I have time, that is the first phase. For the second phase, if we have time, I can also go over the second phase, which is about the analytical modeling of another type of the harvester, which right now I'm working on it, and I hope to get a larger power compared to the one we have in the first phase. And the last thing I am going to present comes to introduction. So you know that the number of vehicles across the United States has increased a lot over the past few decades, and the highway statistic, for example, shows that the average daily vehicle mile traveled in the U.S. is more than 5 billion, which is a very large number. And these movement of vehicles over regions especially represent a massive source of kinetic energy, vibration, which is mostly unused in our national transportation network. But the idea is to harvest this energy, vibration energy, convert it to electric energy, and hope be able to power sensors in the solid regions. So these sensors can be used to monitor the bridges. For example, the acceleration response, the strength response, and so on. So here you can see one type of sensor, which is accelerometer. Is a wireless accelerometer. So they don't have any wire. They connect to data library through wireless connection. And this is another one, which is a strain sensor. And this sensor uses a battery to work. But this battery has a limited lifespan. So the idea for this work is to replace that battery, that power source, with infinite power source, which can be harvested from the vibration of the bridge. So the objective of this research project for the first phase is to model, design, and test electromagnetic energy harvester, which can generate a high electric power, and we prefer this power to be about 0.5 watt. It's a little difficult to reach that level, but we are working on it. This amount of power is enough to power conventional wireless sensors we have in market. The next phase is to reduce the size of that device and increase the output electric power density by arrangement of the magnets in linear arrays. So that can help us to amplify the magnetic field, and that also helps to increase the output power. So when we increase the magnetic field, that increases the coupling between mechanical and electrical domains of the device. So this figure shows the different components of this system, self-powered bridge monitoring system. We have excitation, which is vibration of bridge because of traffic. We have a civil infrastructure, which is bridge. When it's subjected to traffic, it has a vibration. We install an energy harvester on the bridge. So this energy harvester in this study is electromagnetic based, which is based on the relative movement between a magnet and a coil. That relative movement generates electric power, if you remember, based on Faraday's law of induction. Then we have output from the coil, which is electric power, electric current, let's say, or voltage. This voltage is harmonic, so it's not direct, it's alternating current, it's not direct current, so it's not stable. The reason is alternating because the vibration is harmonic, so the direction of vibration change, and so the direction of current also change. So the objectives of using AC to DC converter is to convert the AC current to the DC current, and that DC current can be used to power sensors, act just like a battery. Then we need a DC to DC converter, which amplifies the output DC current. And then we need a power source, which is a rechargeable battery. We connect it to the harvesting circuit to store the energy, and then we connect that to the sensor. So you can see here we have an input, and that input is the vibration of the bridge because of traffic. Traffic induced vibration, and we have an output, and that output is power, electric power. We can connect this system to a sensor, and that sensor can measure the vibration or the, let's say, other response quantities of bridge, like displacement, strain, temperature, and so on. In this project, we focus on only one part of this system, and that is the designing the electromagnetic energy harvester part. Of course, the other part also can be investigated, but the other three parts, for example, this one and this one, is the current and battery. We model them just using a very simple electric system, which are very quick. Theory and basic concept of the device. So this is the analytical model we developed to study this device. Here we have a coil. You can see this coil here. The plane of the coil is normal to the page, okay? The slide. So that we have a damper and we have a spring. That damper just is there to simulate damping in the system. Any dynamic system has a damping. So we have to, in the mathematical formulation, we have to consider that damping, which we do it using that damper element. And we have a spring. A spring can be physical. I'm going to show you later. We model the spring here using real spring. real world, and for the field testing and laboratory testing. And so this coil is connected to the base. That base here represents the bridge. It's connected to the bridge, and that base is moving with the harmonical motion, which is UBX T. So we assume that U is a sine wave. It's a harmonic simple sine wave. Of course, can be random motion, because traffic is not really harmonic and cannot be predicted. But we, for simplification and just theory, assuming a simple harmonic motion, which is sine wave. And we have two arrangements of the magnet, one on left and one on right. And this shows the arrangement of the magnet. So these are magnets, permanent magnets. So when this coil moves with respect to those magnets, that causes induction of a current inside the coil. Okay, then that current can be harvested for the powering sensor. And if you remember, I just said about the harvesting circuit, and this part is the harvesting circuit. We replaced the converters, AC to DC and DC to DC, just with one simple resistance, which is we call it load. So this is the general view of the analytical model, which we are going to study and develop equation for this model. And this figure, this model actually is a simplified dynamic, coupled dynamic and electric model of the device. So we have a single degree of freedom system, dynamic, mechanical single degree of freedom system, the one with mass, and we have one electric circuit which is attached to that mass, and that circuit actually represents the coil and the electric harvesting circuit, and that R, as you just remember, is the resistance of the load or harvesting circuit, and this moves with respect to magnetic field of the magnets. So that is the frequency of the vibration of the bridge, which is why it should be FB. And this also shows the parameter of the coil, which includes resistance and induction, which I don't want to talk much about them because they're just numbers and we can calculate them based on the shape of the coil. So what are the steps we have to take to characterize the behavior of the device? The first, or develop the equation, governing equation. The first thing is to find the formula for magnetic field of the magnet, which we should with B vector. The second thing is to develop analytical model for the coil, and the third step is to develop a formula to simulate the magnetic interaction between the magnets and the coil, which we should with a force parameter. And lastly is the electromechanical governing equation, which we solved that equation in MATLAB based on the parameter we chose for the device. So if you remember, I said we have two array of magnets on the left and right side of the coil. When we can change the arrangement of the magnet, the pole arrangement. By doing that, we can change the magnetic field of the magnet, and and that helps to amplify the magnetic field and the output electric power. But which one causes the maximum electric power? We have to do analysis. This is the uniform array. The second one from the left is the X linear alternating array. So when I say X is the vertical one downward, this is the direction of motion. That means the coil moves in this direction. So this is X linear alternating. This is the third one is Y linear alternating, and the fourth one, the last one is planar alternating arrangement. We have to study these arrangements. So this is the first step we have to take. So how we can model a magnet. My major is structural engineering, civil engineering, just like you, but I spent all my years of PhD to study magnets. So probably you have some basic knowledge of magnets, but my knowledge was basic when I started. So, but it's very interesting topic. So I don't want to go through the theoretical part. Just want to show you that we have a governing equation for magnetic field of magnet, okay, which is shown by this equation, which is based on Maxwell equation, if you remember. Maxwell equation is our equation which governs the magnetic field and electric field, magneto-electric field. So this B stands for the magnetic field of the magnet, one magnet, and is a surface integral. If we take the integration over the surface of the magnet, okay, in the coordinate system, this coordinate system, we get this formula. So this is a function in terms of x, y, z in a space, and give us the magnetic field in each point of the space around the magnet. So this is for one magnet, but for array of magnet we superimpose. We sum all the magnetic field of the magnets, and we get this formula in x and y direction. So this is total magnetic field of array, one array. So the second step is to how to model the coil. The methodology we use is to simulate a coil, a thin layer of a coil, to treat it as an equivalent magnet. Okay, we can do that. So for each layer of a coil, you know the coil, we have a couple of layers. Okay, for each layer we can treat it as a one equivalent magnet. Okay. And then use the equation, use the function we developed in the last slide to find the magnetic field of the coil. We find the magnetic field of the equivalent magnet, and then we find the magnetic field of one layer of the coil. If we sum all the layers, we get the magnetic field of all the layers and the coil as a whole, which is this equation. C stands for the coil. So how we have coil, we have the magnetic field, we have magnet, but how we can find the interaction between them, because they have interaction, they apply force to each other. That force can be found by Lorentz force law in physics, which is this equation. Again, this is the integral, surface integral. If we take this surface integral over the surface of magnets, we can develop this equation in terms of parameters, geometrical and magnetic parameters of the magnet and the coil. And finally, we can find the total force applied to the coil, or opposite of this force, opposite direction is the force applied to the magnet. They act based on the third law of Newton, action and reaction. So this is the total force applied to the coil, which has three components. Is in a space, x, y, and z. If you remember, I said this coil moves in x direction. So we don't need y and z components of that force, interaction force. We just need x component. So that x component appears here. We have it here. So I don't know how many of you know about this equation. This is the equation of motion of a single degree of freedom system in structural dynamics. It's in each direction, and we have this force applied to the mass, which is the mass of the coil, and this is the force applied to that single degree of freedom system. And of course, we have one equation which represents the generation of electric current in the coil and the harvesting circuit, which we describe it by this equation. These two equations are coupled. It means that they are not separated from each other. If one equation changes, the parameter of one equation changes, the parameter of other equation also change, so they are coupled. And the coupling happens because FCX, that force. So we can show that FCX, that force, is proportional to electric current with that K factor, which we call it, it's a very important factor in studying electromagnetic energy harvester. We call it electromechanical coupling coefficient. So we have to, if we find that coefficient, then we can put it here and we can find FCX. So you can see here in this equation, which is mechanical, describe the mechanical behavior of the system. We have I, which is current, and also here we have I, which is current. So you see these two are coupled through that electric current. And that coupling actually is represented by that K factor. If K is 0, so they are decoupled, we don't have coupling. I'm going to explain when K is 0 in the next slide. So we developed this again formula to find the Kf in terms of the geometrical parameter of the coil. And then we can find the induced voltage using this equation from electromagnetism. Again, you see this equation also can be this voltage can be represented by the K factor, which is K factor multiplied by the velocity of the coil. So voltage is proportional to velocity, force is proportional to the current. That is why they are coupled. So as I said, this is for the first equation for the mechanical domain, the second equation for the electrical domain, and they are coupled. But we can simplify those coupled equations more by using this equation. If we represent current in terms of velocity and resistance and K factor, then we get only one equation. But you can see the damping here, damping term changed. This damping here, if you remember I discussed damper. Damper is a device we use to dissipate energy. You know that in vehicles, we have dashboard that dissipate energy. So here we have, any structural mechanical system has damping. So that damping here, that represents the damping in mechanical system, and this part represents the damping because of the interaction between mechanical and electrical domain, which is called eddy current damping. So these are the parameters of the equations. What I need to do, so this equation represents the behavior of this, the device. We want to generate power, okay? So I have to solve this in MATLAB. Then after solving, I find the current. Then I can get the electric power. This electric power is represent the output power from the energy harvester, which can change by vibration of lead because of the traffic. And we can, that is instantaneous power. It's better to use average power over the time we consider. So this is the parameter we choose for the system to solve that equation. The most important parameter we have is the frequency of the base emission, which represents the frequency of the bridge with 3.5 hertz, and also the amplitude of the acceleration of the bridge, which is we assume because of traffic we assume is 0.05 G, is very small, and parameter of the coil of the device of the magnet and the coil, which are here. Yeah, so as I say, the system is subjected to a base emission, which is harmonic, a sine wave. You can see it here, and with this amplitude of acceleration and this frequency 3 hertz. So one important point here, many of you probably know resonance condition. So when we have a resonance, so it means that the amplification of the displacement increase over time. Okay. To increase the output power, we have to make sure the system, the harvester, is resonant with vibrational bridge. So that is why we assume the frequency of the system also is 3.5 hertz, same as the frequency of the bridge, to make sure this happens in resonance. In reality, it's difficult to reach to this condition, but in theory we can do that, because in reality it's difficult to measure the frequency of the bridge. Then we have to design the device based on that frequency, and many bridges have different frequency. It is not economical to design for each bridge one device, with own frequency. So in reality it's difficult, but in theory we can do that. So in this study we assume the frequency are same. We have analytical model, so we have developed based on theory. Okay, we have to prove that it's correct. To do that, we have to use finite element simulation. So finite element simulation is the most accurate method we have to describe the behavior of the system. Here we developed a simple finite element simulation. Those are magnets, and that is the coil. And this coil moves with respect to those two single magnets. This is just to validate the formulation we developed. And you can see the black line, this one, this is from an analytical model in MATLAB we solved, and those dots, those stand for the result we got from the finite element. You can see at this time, they are quite same and they are matched. So we can say the model we developed, analytical model, is quite accurate. So we can go forward to do parametric analysis. So before we do the parametric analysis, if you remember, I told you about this K factor. You see the K factor is changing by time. In many studies, they assume is constant because it's very difficult to find K factor analytically. But in reality, it changes by time. K factor at the where the coil is in initial position is 0, but when the coil moves far away from the magnets. Okay, magnets are here and the coil are here. You see, they are very far. The coil is far from the magnetic field of the magnets, so they don't have any coupling. And you can see when this happens, this K as a function will reduce, which makes sense with the reality. And the two systems will be decoupled. So here we do the parametric analysis, and you have to remember that our objective was to find what type of arrangement caused the maximum output. Okay, we developed all these formula, we validated to find out what type of arrangement caused the maximum output. So this is the analytical model of the system, and these are the parameters. We changed these parameters. We assume other parameters are constant. We changed the magnitude of the acceleration, which is vibration of bridge. For example, for heavy traffic, we have larger vibration. For low traffic, we have a lower vibration amplitude. We assume the two systems are in resonance, And also we can change the resistance of the harvesting circuit. We can design different harvesting circuit, different converters. So that helps us to change R. So that is why here also we choose R to be a variable for the parametric analysis. So we did the simulation for this 4 type of arrangement. This is uniform arrangement for 3 magnitudes of 3 amplification of the vibration. The top one, this one is for 0.1 G. This one is for 0.05 G, and the other one is 0.01 G, which is very small. So the vertical axis actually is a log based on log logarithm, and the reason is that the output of, for example, this one, the power output from this array is very, very large, and we couldn't compare, so we compared with the other one, so we wanted to use a logarithm scale on the vertical axis. You can see this one, the uniform array. In case of the maximum amplification, the output power is almost about, let's say, 1 milliwatt. And doesn't really change when we change the R, the resistance of the harvester. And we can, for this one is very small, even smaller than uniform. For this one is okay, but for this one has the highest electric power, output power. So when we want to design the device, we have to use this. Okay. But I'm going to explain next slide. We fabricated the device not based on this one, but based on this one. The reason was we had some difficulty to attach the magnet to each other. We didn't have some tools in lab to attach them to each other because they are very strong and they seldomly move because of the force they apply to each other. But in this case, they are in a static equilibrium, so it's easier to attach them to each other by hand. So, but our formula, our mathematical model shows that this arrangement can cause the highest amount of electric power. And you can see for 25% of RC, RC is the resistance of the coil, we can get 0.5 watt output from the harvester, which is what we were looking for. But this is in theory. In reality, maybe can be difficult. We have to work on it. So based on the model we developed, so we wanted to test if we can fabricate a device to see if it's working or not based on the model we developed. So this is a proof of concept model, actually a prototype. So the dimension is very huge, it's not optimized, but we just wanted to fabricate it based on the formulation we developed, and just to see if the system is working or not, and this is a proof of concept. In the second phase, we want to reduce the size and increase the electric power density. So this one shows the 3D model of the device, and this is the setup of testing the device in lab. You can see those two actually shows the magnets array, left and right, and you can see we have a spring. You just remember I talked about the spring. These spring represent those springs in the model. And we have accelerometer. This accelerometer measures the acceleration of the base, which is this base actually represents the vibration of the bridge. Okay, and we have a shaker. Actually, it's an actuator. That shaker simulates the vibration of the bridge. So that shaker is connected to that base, and that base is moving. All the system is moving, and that causes a relative movement between the coil and the magnets, and that causes induce electric current. As I said, we wanted to use this arrangement which caused highest amount of power, but we couldn't because of some technical issues in the lab. But we use this one, which is easier to work on it in the lab. And so this, you see, this is the magnets we use, and this magnet arrangement are based on this arrangement. They are 0.5-inch magnets, small magnets. And this is the coil. So this coil is moving with respect to these two magnets. And this is the system we have. And we measure the output, including the acceleration and the voltage, using this data logger. And we process the data in computer. So this is the one example of the movement. I can show you here. So you see that is the movement of the coil with respect to the magnets. That movement causes a generation of electric power. We tested this on a bridge also. We are going to show that this is in the lab. So what we got? This is the we did the experiment for 5 almost different motion. There was a sample for issue with the actuator. We couldn't generate a wide range of the motion with different frequency, but we got the frequency we got was from 1.6 Hz to 3 Hz, which is not very close to the frequency of the system, which was 3.5 if you remember. But anyway, we got this output for the electric voltage, and then the root mean square of those voltage. You see, it's very small in range of millivolt. But and the reason, if we could use the optimized arrangement to increase the output, but we use different arrangement. But again, this is the output of the system. And the last step for phase 1 was to test the device, a simple test device on a bridge. We did it in New York. I don't know if you have been in New York. This bridge is a bridge connecting kind of Manhattan to Brooklyn or Queens. So we worked there, and is Robert F. Kennedy Bridge. We tested there. We installed the device on a beam, which is part of the deck of the bridge. Yeah. So this is the tablet, laptop we have. We had also a small data logger. We connected the coil to that data logger, and whole this beam actually was vibrating because of the traffic. Traffic was passing over actually overhead, and we got this result. And this is the output of the device, which is again is very small, but promising for the next step of the work. And you see, this is random because it's in reality is random. But in the formulation we developed, we assume it's harmonic. It's simple harmonic with sine wave. But in reality, you see, it's random. Let me show you the. That is the vibration of the bridge, and that is the output we get, electric power we get from the device at the same time. The bridge is moving because of the vibration. It's very small. You can compare it with the vibration in the lab. It's very small. But this design is not optimized. We can optimize it to increase the vibration amplitude by putting the device in resonance with the bridge. Yeah, thank you so much.